In this video, we're going to discuss the boundary of a set in a topological space. Here's our definition. Let x tau be a topological space and let A be a subset of x. A point x is in the boundary of the set A if x belongs to both A closure and x minus A closure, or in other words, A complement closure. So we kind of intuitively think of the boundary as being, things that are both in A or are limit points of A and are in X or in A complement or are limit points of A complement. So that's the definition. Recall that A closure is A union A prime, A together with its limit points, and X minus A or A complement closure is A complement union A complement limit points. So we sort of intuitively think of it being like boundary like that. Again, this is the same definition as we had in a metric space. So here's a theorem about the boundary of a set. Some of these ideas, again, were discussed previously in terms of metric spaces. Anything that we proved previously still applies, but a lot of this we did not formally prove. So let's look at this theorem. First of all, the boundary of A is equal to A closure intersected with A x minus A closure. This is just the definition. And that's also equal to the boundary of A complement. So we see that just reversing the roles of A and A complement gives us that this is a clear equality. Next, the boundary of A, the interior of A, and the interior of A complement are pairwise disjoint sets whose union is X. In other words, these three sets partition the set X. Proving this is going to be homework. Part 3, the boundary of A is a closed set. This is immediately obvious. We know that the closure of any set is a closed set. So A is closed, X minus A, or A closure is closed, X minus A closure is closed, and a intersection of closed sets is closed. So this tells us that A closure intersected with X minus A closure is closed. So that's immediate. A closure is the union of the interior of A together with the boundary of A. We will prove this one below. Next, A is open if and only if the boundary of A is a subset of A complement. This is going to be a homework problem. 6, A is closed if and only if the boundary of A is a subset of A. We'll show this one below as well. And 7, A is open and closed if and only if the boundary of A is equal to the empty set. And again, we'll show this one below, assuming that 5 and 6 are true. So let's now prove part 4, that A closure is equal to the interior of A union with the boundary of A. So to show this, we are going to do this as two set inclusions. So first of all, let's suppose that a point X is an element of A closure. So if X is an element of the interior of A, of course we would be done. It would be in the union of those two things. So otherwise, if it's not the case that X is in the interior of A, we want to show that X is an element of the boundary of A. And the boundary of A, we know, is A closure intersected with A complement closure. So we already know that X is in A closure. That was the assumption that we made. So in this case, we would want to show that X is in the closure of A complement. All right. Again, if X is in A complement, we are done. If X is in A complement, of course we're done because A closure complement is A complement closure is equal to A complement union the limit points of A complement. So if it's in there, we would be done. Otherwise, if it's not in there, then what would be the case? So otherwise, what we have is that X is not in A complement, so X is in A. And we also know that X is not in the interior of A. So X is in A and X is not in the interior of A. If X is not in the interior of A, that means that there is no open set U such that X is an element of U, which is a subset of A. To be in the interior means there is some open set containing that point that is completely a subset of A. Hence, not being in the interior means no such set exists. So that means that for any open set U containing X, U is not completely contained inside of A. So that means that there exists some Y that is an element of U and is also an element of A complement. Since X is in A and Y is in A complement, that means that X and Y are not equal. So what that tells us is for any open set U containing X, the intersection of U minus X and A complement is not the empty set. In other words, that means that, therefore, X is an element of the limit points of A complement, which is a subset of A complement closure. So we have shown that if X is an element of A closure, then X is either in the interior of A, or if it's not in the interior of A, then it's in the boundary of A because it is in both A closure and A complement closure. The reverse inclusion is a lot more straightforward. So for the reverse inclusion, we know that the interior of A is a subset of A, and that's a subset of A closure. And we also know that the boundary of A is equal to A closure intersected with A complement closure, which is itself also a subset of A closure. So since each of these things are a subset of A closure, therefore the interior of A unioned with the boundary of A is a subset of A closure. So we've shown the inclusion, the set inclusion in both directions, and we're done. So that's part 4. Part 5, as I said, you're going to prove part 5 for homework. And for part 6, assuming that part 5 is true, let's now prove 6. So we're going to prove this using the duality between open and closed sets. We know that a set A is closed if and only if A complement is open, and then by 5, that's true if and only if the boundary of now A complement is a subset of X minus A complement. What is X minus A complement? X minus A complement is A, the complement of A. And so that's exactly what we wanted to prove in part 6. Great. Now to prove 7, this is just as easy, assuming that 5 and 6 are true. A is open and closed if and only if both of these things are true. So A is open and closed if and only if the boundary of A is a subset of both X minus A complement, and A. What's in the complement of A and A? Nothing is in there, so we're done.